So I've decided to do some of the example problems or the sample problems in class 11 for ES110 as videos. So I'm going to make all of these. I think there's going to be 4 of them. Is that true? Yes, 4 of them. Let me close my door so people don't hear me talking too much. Okay. So I'm going to do this in my own way, slightly different from what's in the book, but I do encourage you to read the book's version, and either way is actually going to be okay for us. So some preliminary things. They tell us about the weight of that the crane right here is going to be 1,000 kilograms. And the crate is 2,400 kilograms. I want everything in newtons because we're going to deal in forces, so I'll get that out of the way here. And so 9.81, it's going to be the weight of the crane, 9,810 newtons. And actually the book does it with kilonewtons, which is actually going to be a little bit more convenient. So it's an obvious conversion there. So I'll stick with that, 2,400, 9.81, and I can just say it'll be 23,540 newtons, or obviously 23.54 kilonewtons. And let me, this just gets some preliminary out of the way. We want to determine the components of the reactions at A and B. And we look closely, we can see that A is a pin joint, where B is like this little rocker joint. And that rocker joint, if we recall from, oops, I'm going in the wrong direction here. Using the wrong mouse. If we look back up here, we can see that this kind of joint, I think it's right there, that rocker joint, it only has a force in the perpendicular direction there. So that's something to keep in mind. And so I always label an FBD, just declare that this is an FBD. And we want to draw this, and I'm going to draw it without the hanging weight onto the thing. And I guess I have kind of the basic thing down there, and then I like to put my loads. Sometimes I like to change things into the red color for this. So this load over here is going to be our 23.54 kilonewtons, and then this load is going to be our 9.81 kilonewtons. And I like my reactions to be this way. If you don't know the direction that a reaction is going to go, I always decide to go positive. And by the way, one thing that's always good is to declare what is going to be the directions, so they coincide with the equations that you use. So I'm going to say there's a reaction in that direction, just like we noted just a second ago, but there's none in the vertical direction onto here. It's just pointing away from there. I don't like using the reactions, the letters like they usually do, but I did on my page, so I'm gonna go this way. What I usually like to do is use R's. So maybe I'll try to do that, even though I have it on my page. So this is going to be the RBX, right? And then I'm gonna choose positive at A. I kind of know it's going to be the other direction, but we're going to pretend, because if we don't know the direction of something, choose positive. And right here, so this is going to be R-A-Y, and I like to pronounce that. That's Ray, and then this is R-A-X. It's Rax. It's Rax and Ray. I don't always do this, but it does say in the book that you should. So let's do this, is to put the necessary dimensions. You don't want to put all the dimensions that exist onto the thing, only the ones that you need. Now, you might not know that to start with when you're looking at the problem, but if you can figure out that you're not going to need to know a particular dimension, then don't put it on there. We're going to need all these for the moments. All right, so there is a free body diagram, completely done and completely labeled. Sometimes people will put labels or put the variable symbols on there instead of the numbers, but I tend to do it with the numbers. Okay, so we start out, now our strategy here, we got to think about strategy, is we don't know RBX, we don't know RAX, and we don't know RAY. Those are unknowns for us. So when we have that type of situation, which is very, very common, what we want to try to do is get rid of some of the unknowns and then just focus on one particular unknown. In this case, we could actually pick either location. I'll explain that in a second. But let's pick this A, because it has 2 right there. We could pick B as well. Maybe I'll explain that now, because RAY passes right through B. So it too is a good choice. So we just want to eliminate essentially RAX by picking A. Right, because now RAX goes right through that point that we're going to take the moments about. So we're really doing this on purpose so we could solve for RBX. That's a strategy. So if that wasn't 100% clear, it's because I just mushed it up. But it is something that we want to try to work towards. So if you didn't quite understand it, have no fear. We're going to do this a lot of times, and it'll become clear to you that that's a part of our solution strategy, is to pick a point to take the moments about. And we selected A. So I just marched through here. I'm going to pick this 9.81 kilonewtons to look at first, and we can see that the moment arm is going to be 2 meters, right? And it's going to be going clockwise. So 9.810 and then times our 2 meters. And let's go to the next load right here. We see 23.54, and that too is going clockwise. And its distance now is going to be 6 meters. And now we go to the reaction, and we can see that the reaction at B, as drawn, goes counterclockwise, right? It's going wee right around A. So, and it's going to make that noise. RBX, and that perpendicular distance to that reaction force is 1.5. So doing this math here, we end up with 107.2, and these are kilonewtons. Remember that we used all the forces were kilonewtons, all the distances were meters. Of course, all of those meters are just going to cancel out, so we have a kilonewton as our answer, and it was positive, so we could go ahead and box that guy out. That's one of the things that we want. That's a reaction force at B in the X direction. Now, in the Y direction, we actually didn't need the moments for this in the Y direction. Just looking at this right here, we say the sum of the forces in the Y direction equals 0. Declare upwards as positive. And I'll just look over there, the reaction. We have the RAY is pointed upwards as drawn, and then the 9.810 is downwards, and then the 23.54 is also downwards. So we get RAY is going to be where's the number? 33.35 kilonewtons, and that's upwards. Lastly, we want to know RAX. And we actually have a choice in this, but the simplest one, and the one you'll do most often, I'll do that first, is some of the forces in the X direction. Right? And then as I've drawn it, I drew it as in the positive direction, so RAX. And then I know RBX, I just found it up around, and that is in the positive direction, 107.2. And you'll look around, and there's no other forces in the X direction. Therefore, RAX is equal to negative 107.2 kilonewtons. But that means that we chose poorly, that we guessed wrong. So we could say, if we're going to give the final answer, I want it with an arrow. I don't, just not X. I want it with an arrow. I don't want it with a sign. So we go 107.2 kilonewtons that way. And so that would be the answer. So we've answered the question. But what we could have done instead right, is to now, let's say the alternate thing from this right here, we could have taken the sum of the moments about B instead is equal to 0. And now we're going to take it about there. What we would say is negative R, well, as shown, as drawn up here, R, negative RAX times our 1.5, right? And then we have a negative 9.810. You could see that that's also going to be about 2 meters. And then it's also a negative 23 because this is clockwise as well. So they're all clockwise. So you can, and it's going to be times 6. So you can see that what we would end up with is a reaction there was our negative 107.2 kilonewtons, right? Just like what we got up above. But remember, we don't want to report it with the negative sign. We've defined what's positive. It's two-dimensional, so we know we could use the arrows up and down. So that's going to be the 107.2 kilonewtons, and that away is because it's in the negative direction. So that was sample problem 4.1. Take a look at the book. Read their version of the thing, or their approach. And I think I would rather you gravitate towards mine, but I'm not going to, what they've done is fine. But you'll see that this is a very much a standard approach, a problem that we will do many, many times in many different classes.